Let us discuss about gravitation. It is the fundamental force of attraction that exists between all particles with mass in this universe. And it is the weakest of the four forces, and the particles which are responsible for this force between any two bodies are known as gravitons. The law of attraction of this force was proposed by Newton, and according to this law, if we have two masses or two bodies, let us say body A, which has mass m1, and any body B having mass m2, and distance between their centers is, let us say, d, then the force of attraction between these two masses according to Newton is, this F is directly proportional to product of these two given masses, and this force is inversely proportional to the square of the distance between the centers of these two bodies. Now, if we combine these two statements or these two conditions, then we get that force is proportional to the product of the two masses and square of the distance between the centers. And if we write this equation in terms of equality, we can write F is equal to, then we have to put some constant of proportionality, and in this case it is written as capital G, and remaining items m1 and m2 as it is, divided by d square, where this G is a constant of proportionality, and it is known as universal gravitational constant, and it is really constant because it has a fixed value which is 6.67 into 10 raised to the power 11 Newton meter square per kilogram square. So that is the value of this constant. Now this force will depend upon the masses of two bodies and where they are lying in the universe. That will determine the force. This force may be, for example, we can say between Sun and Earth. It may be between proton and proton. It may be anybody on the Earth, body and Earth. It may be between Moon and Earth. So like this, you can mention not many examples in which this force can be mentioned, or we have mentioned in the equation that this force is between every two particles in this universe. And since this force is everywhere in the universe. Therefore, this law of force of attraction is also called universal law of force. This is a universal law of gravitation. Now, as I have explained in above example, that if we have two bodies like this, m1 mass of first body, m2 mass of second body, which are interacting with each other, and according to this law, the force acts between the line joining the centers of these two forces, and this force is along this line all the time, and therefore due to this characteristic it is also called central force. And since this is central force and acting along the line joining these two centers, so force of m1, force of attraction of m1 on m2 is equal to force on m1 due to m2. Or you can say, if m2, this m2 is exerting a force, that is force on 1 due to 2, and similarly let us say force on 2 due to 1 is F21, then according to Newton's third law, force F12 will be equal to minus force F21. That means these two forces are opposite but equal to each other, which means that if I take sun and I take earth, then the force which sun is exerting on the moon, on the earth along this line, means force which earth is exerting on sun, that is earth on sun, will be equal to the same force which sun is exerting on the earth, which is, you can say, force of sun on earth. So these two forces are equal, but naturally they are opposite in direction, because that is attractive force. These two forces are attractive forces and they are equal. And similarly you can mention that a person standing on the earth, then the force of attraction on man due to earth will be same as force on earth due to man. So these two forces will be equal, but of course they are opposite in nature. Now since this force is central force, so there are few characteristics of this central force, and these characteristics you can mention as, one is that this force always acts along the line, acts along line joining centers of two bodies. first characteristic. Second is that this force is conservative force. This is a conservative force. The meaning of conservative force is that the work done by this force, let us say work done by this gravitational force in moving a body by certain displacement or distance, is independent of the path followed by this object in moving this distance x. For example, if on a building you have to on the earth you have to bring this mass to the top of the building, then you can bring this mass through the stairs, or you can bring this mass through a ramp, or you can bring this mass by lift over here. But in every case, the distance traveled will be the height of this building, and therefore the work done will be equal to mg, that is weight, multiplied by height. This will be the work done, and this work done does not depend how you are bringing this mass up to here, and since it is independent of the path followed by this object, therefore this force due to which this work is done, this force is called conservative force. Then third characteristic which we can mention is that this force is long range force. Long range force. The reason is that force is inversely proportional to square of distance, and naturally if you increase distance to a large extent, then force will become weak and weak, but it will never be zero, because it will be zero only if d is infinite, and therefore we consider it as a long range force. The next characteristic which we can mention is that gravitational force, this central force, can be derived from scalar potential. That means this force can be derived from scalar potential. Now what is the meaning of it? Suppose we have gravitational potential which is given by minus g m1 m2 over r. This is scalar quantity because nothing is vector here, and this is a potential. Now if I differentiate it with respect to r, then I can write du over dr, and its differentiation with respect to r will be equal to minus g m1 m2 over, so it's 1 over r differentiation is minus r square. That means this minus and 1 over r square, this minus cancels, and which gives you g m1 m2 over r square, which is gravitational force, and we can write it as F. So therefore we have derived this force from this scalar potential. Therefore we say that central force can be derived from scalar potential. Another characteristic which we can add in the list, that is, in central force motion, the angular momentum of the system, of the particle, is always conserved. That means we can say angular momentum is conserved. Is conserved. The meaning of it is that L is constant in central force. That we will explain in due course a little bit later. Then next characteristic which we can mention here is that central force obeys inverse square law. Inverse square law, which means that if distance is increasing, then this force decreases with inverse of the distance between, inverse square of distance between the centers of two bodies. So these are the 6 main important characteristics of this central or gravitational force, which is of course a central force. Now let me explain why we say angular momentum is conserved in central force. Angular momentum is conserved in the central force. That can be explained like let us take the example, then let us take the definition of angular momentum, and according to definition, angular momentum is given by R cross P, which is we can take from this diagram that suppose a mass m is in the motion, rotational motion, let us say, about this axis of rotation, and it is at a distance r from here, that is this r, which is perpendicular to this axis of rotation. Let us say it has motion along the perpendicular to this r, and this velocity is v, and I assume it has mass m. Then the momentum associated with this mass will be p, which will also be in the same direction, 90 degree to this r. Now if it is so, here r coming from here, p is from here, and we can also write it is equal to r p sine of theta, and this theta is between the velocity or momentum vector and this r, and naturally I explained this r and v are perpendicular, so we have 90 degree angle here, so sine 90 will be 1. It comes out to be rp in magnitude if you want. But let us take the example from here. Let us explain from here. R is equal to r cross p. Let us differentiate both sides with respect to time. These 3 vectors, we differentiate vectors with respect to time. We get dl over dt is equal to d by dt of differentiation of this, that is r cross p. These are 2 variables which we can write dy dt differentiation of first function, first variable, into second will remain as it is, plus first variable as it is, then differentiation of the momentum vector with respect to time. So this is dl over dt. Now from this equation we know that according to Newton's second law, dp, rate of change of momentum, it is equal to force, and this dr by dt, that is rate of change of displacement, dr by dt, rate of change of displacement is called velocity, and if we substitute these two values here, we get dl over dt, that is rate of change of angular momentum, is equal to dv cross b over dt. Oh, I'm sorry, here we have not to write this dv dt because I have already differentiated it. We will write this as v and this as b plus r cross, this is our force, that is F. Now this expression further, this is V, but P is also M into V. So if I write it as V cross M into V, this P is MV, plus R cross F. Further, it implies dl over dt is equal to, since here mass is constant in the Newtonian mechanics, so we can take this mass here outside of bracket. We can write V cross V plus next term R cross F. But here V cross V means this is a vector which is multiplied by itself, and the angle between the vectors is 0, and here sine 0 will be 0, therefore V cross V will be equal to 0, and therefore first term will become 0, and so the term of angular momentum that comes out to be further dl over dt will be equal to R cross F. So that is the value we get, and of course the R cross F is called torque. You can say it is also equal to torque. But in case of central force, when this force which we are discussing here as a gravitational force, and we have said that F is central force, and we know central force acts between the centers of two bodies, and in this example we have one body here and another body will be here. Between these two bodies there will be the gravitation force, and naturally this force is along the centers of these two bodies, and we say this force is also along this direction, along R, which means that the direction of F and direction of R is same, and if it is so, then R cross F will also be 0. Therefore we can write dl over dt is equal to R F sine 0. It means total is 0. Now from this equation we can immediately check that if the differentiation of something, that is angular momentum, is 0, which means differentiation means change in something is 0, it means it is not changing, and when it is not changing, then we say it is constant, and it implies that this quantity here, which is angular momentum, that L will be constant, and this is constant only if this factor is 0, which means the torque is 0, and therefore we conclude that angular momentum is conserved in the gravitational force motion because there is no external torque acting on the particle on the body, and that is why we say that angular momentum is always conserved in the central force. So this is fifth line, fifth characteristic, which is about the L is equal to constant or angular momentum is conserved. So this is about the gravitational force and law of gravitation and main points about the gravitational force. In the next video, we will discuss the equation of motion under central force. Thank you for watching this video.